This is Nullspace Prep, our fully featured CAD and meshing pre-processing platform. Within Nullspace Prep, you can create and manipulate your CAD, perhaps modify mechanical CAD that has come in from your mechanical team to prepare it for simulation. If you're a designer, you can create the designs from scratch, and we'll just work through a few examples here. So over on the right-hand side under the command panel, one of the main options that you're going to be using is the entity option. Underneath entities, you have options for volume, surfaces, curves, and vertices. And under each of these, you'll find a series of action buttons. So we can create your typical primitives. You can provide some parameters to control their size. You can perform Boolean operations between them, and you can even perform more advanced features such as filleting. And then, perhaps we want to make a copy of this geometry, so we go through and select the geometry. The size of the box was 10. I'm going to space it out 12, and maybe we'll make several of them, and then we can zoom out and we see now we have 6 of these. One of the really powerful features about Prep is its ability to perform CAD cleanup operations. So let's say that we had imported this geometry, and these holes represent fastener holes. And we've determined through our engineering expertise that these aren't needed. So I can select the 2 surfaces that represent one of these holes, and when I right click, there's an option here, select similar surfaces, and Prep will automatically find all of the surfaces that are like that. Then you can right click, and at the bottom of this menu there are a couple of cleanup operations that are context aware. In this case, Prep knows that you're dealing with surfaces, and so 2 of the options are remove and composite, and we want to remove, and you can see it automatically removed and filled in those surfaces. So that's a really powerful cleanup feature, and there are a lot of other cleanup capabilities within Prep that you can explore through the documentation and other tutorials. Another useful feature within Prep is the fact that every action that you're performing in the GUI is actually just issuing a command behind the scenes to the CAD engine, and those commands get echoed out to the command window here at the bottom of the interface. And you'll notice there's a history tab, and you can see a history of all of the commands that have been issued in the session since you started. And we can take these commands and paste them into what we call a journal file. And this journal file can be replayed, and we see we got right back to where we just were. And as you're going through, a very typical workflow would be to use the GUI to rough in a design if you're doing a design from scratch, or if you're exploring the best way to do CAD cleanup, to run through different ideas about how to remove features and things like that. And then we just copy those commands into a journal file like this for replay. Now let's say that we were creating geometry, and we want to parameterize that geometry. Maybe we want to parameterize the size of the hole in the cylinder, and maybe even make the fillet size dependent on that radius. And now when we replay that, we get one box with a bigger hole and a radius that is dependent on the size. Maybe let's even add a second parameter And then we can replace that here. And we see a different size for our fillet there. So you can let your imagination run wild as to how you could begin to build up more sophisticated geometries and then parameterize those geometries and use this workflow as a means for building up parametric studies or design optimizations or even uncertainty analysis. Now, all Nullspace products provide an end-to-end Python API that ultimately supports design optimizations, parametric workflows, automated geometry creation, etc. And you can begin from this journal file to convert your scripts into Python scripts. And there's a convenient button here to just convert this into the beginnings of a Python script. And so we can do a little mild editing here to, say turn this radius into a proper Python variable, turn the fillet size into a Python variable, and then convert these two lines into F strings and replay that, and we get exactly back to where we were. And this Python environment is fully featured. You can import modules, do all of the things that you would expect to be able to do in Python, for loops, if statements, etc. And you can craft all of that directly here within the journal editor. There is also a method for running prep in a headless mode where you can take these scripts outside of prep, run them through your own Python environment. You're just importing the necessary Python modules into your Python environment to be able to run prep either with the GUI or without the GUI. So in this video, we're focusing on how Nullspace Prep and Nullspace ES can be used together to support ion trap design workflows for the ion trap quantum computing community. So let's take some of those concepts that we've just been introduced to and look at how one might parametrically set up a surface electrode ion trap. So here I've got an example. This is actually one of the examples that comes in our user guide. And if we play that, we see we've got a linear ion trap. Turn the mesh off briefly. We've got a linear ion trap with a central ground electrode, two outer wing ground electrodes, RF electrodes, and then DC pairs of electrodes. In terms of meshing, we demonstrate in the user guide a very simple recipe for getting what we might call a physics-aware mesh that's particularly tailored to ion trap type problems. We know that the surface charge density is going to move toward a singularity at the edges of each of these electrodes, so we want the mesh to be fine at the edges and more coarse in the middle of each of the electrodes, and you can see that pattern sort of replicated throughout. And that workflow is enabled by just a few simple commands. We set a size for each of the curves within the ion trap, and then we set a gradient scheme for the triangle mesher. And really these approximately 6 lines, you might modify it here and there for different configurations, but roughly speaking, these 6 lines will serve you very well for ion trap type workflows. In terms of when the solver is actually executing, we excite one electrode at a time and compute the surface charge density that's induced by that single excited electrode with all other electrodes being grounded. And those electrodes get grouped together using this block nomenclature. So block 1 in this case is this central electrode. And if you note, in terms of the CAD, because we drew half the CAD and then mirrored it, there are actually two surfaces here, two CAD surfaces, but they're grouped together into one block. So Nullspace ES is going to view this as one electrode. Similarly, block 2 is the pair of RF electrodes. Since we're exciting them together and we want that excitation as if they were electrically tied together, we group those two surfaces as well. Similarly for block 3, that's the two outer wing ground electrodes, and then all of the DC electrodes are individually blocked such that we can apply control potentials to each electrode and use superposition to synthesize whatever kind of trapping potential we want. Now you'll notice at the top of this script that all of the major variables here are parameterized. So just as another simple demonstration of how powerful this parameterization capability can be, if I just change the number of electrodes, now I have doubled the length of the trap, and you can see it generates the geometry and the mesh very quickly. And maybe I can even double it again. And you see now we have a linear trap with 28 DC electrode pairs. This surface trap is just represented as the surfaces themselves. Typically, you don't need to model the gaps or the depth of the gaps, but if you wanted to, you can very easily, taking advantage of the geometry capabilities within Prep, if you wanted to extend the sidewalls down, so maybe you could study and capture the effect of the sidewalls, we can say we want to create a new surface. We want to do a sweep operation, and we want to sweep all curves. Every curve in the model, we're going to sweep along a vector, say 0, 0, -1, and we want to go 4 microns down. And if we zoom in, now you can see that the electrodes all have sidewalls. So this is a convenient way to model the thickness. If you wanted to model the effect of a ground plane beneath that, with or without the sidewalls, Nullspace ES supports a variety of symmetry planes, and one of those symmetry planes is a ground plane type. The major types of symmetry that are offered are symmetry planes along each of the 3 coordinate planes, and those symmetry planes can have either even or odd symmetry, referring to how the boundary conditions are enforced at those symmetry planes. Nullspace ES also supports discrete rotational symmetry, so if you had a ring trap, or maybe you're doing a Y junction or a cross junction, you can model only the relevant portion of that and speed up the simulation. In this trap, we have left-right symmetry. So I've prepared another script here that takes into account the fact that we only want to model half the trap. And you can see here that we basically have the same thing that we had before, except only half the trap is represented geometrically. Now we can use the fact that Nullspace ES offers even and odd symmetry conditions to synthesize the effect of arbitrary DC electrode potentials, even when we run only half the trap. If you run it once with an even symmetry plane along the YZ plane in this particular example, and then you run it again with an odd symmetry condition, between those two runs in post-processing, you can leverage superposition to synthesize the effect of arbitrary um, control electrode potentials. That can be scaled up to cross junctions or any number of other configurations. And because of the computational scaling that is involved with running these types of geometries, even if you had to run the trap twice with symmetry, that's still faster than running it once with the full geometry. So it's highly recommended where you can to take advantage of symmetry in your traps. As we move toward uh, performing the actual simulation, we need to think about what do we want to get out of this simulation. And typically, we want to get things like potentials, electric fields, and higher order derivatives at points in space above the trap. And so there's going to be some region of space above the trap that we're interested in, and using the Python API, we can define a set of points, either over a 3D rectilinear grid or as an arbitrary set of points where we can ask Nullspace ES to produce the potential or the electric field. If you're interested in higher order derivatives, Nullspace ES doesn't directly output that, but because you can sample potentials and fields at arbitrary locations at arbitrarily fine spacing, the two typical methods that users employ to compute higher order derivatives are either finite differences across a 3D rectilinear grid, or what's a little more efficient is to sample more coarsely and use that data to fit to a spherical harmonic expansion, and then you can compute those higher order derivatives fairly easily. So let's take a look at how to get started with the actual simulation in Nullspace ES. So as I mentioned, all the Nullspace products provide an end-to-end Python API capability. And so instantiating and post-processing with Nullspace ES will take advantage of this Python API. And so we were just talking about sampling points at locations in space above the ion trap. And the way we do that is through a mechanism we call grid files. And so here's an example, a fairly simple example of a grid file. We're giving it a file name and providing some XYZ points. Note here we're just using simple NumPy arrays to specify the X, Y, and Z distribution, scaling that up to meters. Nullspace ES likes to process everything in meters, so we convert everything into meters for those purposes. And then you write a grid. You tell it the file name, you give it a grid ID 0, tell it what type of grid it is, and your two options there are 3D rect mesh, which is a 3D rectilinear grid of points, or polyvertex, which is an arbitrary set of points. Could be a line, could be a helix, could even just be a single point if you know exactly where you want to sample some data. Provide it the XYZ locations, and then this is a flag for overwriting the file. And you can pack arbitrarily many grids within a single grid file. So just as an example, let's say that we were going to add a second grid. I would just give it a new number, change this to false because I don't want to overwrite this grid, and now I would have two grids within the same file. In terms of the actual control settings for the input to the simulation. We use this file that is reminiscent of an XML file. There are several required tag regions. You start with a mesh, you give it a file name, a scaling factor to get it to meters. You can provide a list of electrodes that you actually want to solve for. So if you recall our ion trap, electrode 2 is the RF rail. And in this particular example, we're only interested in simulating the effect of the RF rail. We want to look at pseudopotential. So we're going to filter out all of the other electrodes and only compute the RF rails excited with all other electrodes grounded. And this is taking advantage of symmetry. So we're putting a ground plane underneath the trap. So that's an odd symmetry type, and offsetting it down by 10 microns. And then we have YZ symmetry, which is even. We just simply want to mirror the trap, and that symmetry plane should be applied at the x=0 location. One of the really powerful capabilities of Nullspace ES is its ability to solve very large scale problems, and so we offer 2 solver modes for that. The first is called dense, and so you use that for smaller problems, and that is your typical AX=B, fill a linear system and solve it type of solution. When we move to larger problems, and I'll show you an example of that in a minute, you use our compression-based solver, which adaptively compresses the matrix so that you get a much more efficient memory footprint and runtime for the same problem, and allows you to scale to much larger problems than you would be able to otherwise on a given computational resource. And then you can specify some outputs. So we're going to point it to a grid file and then request that Nullspace ES compute the potentials and the electric fields. And then we also offer output in ParaView format. If you like to visualize things in ParaView, you can output the charge density, and this XMF on tag tells Nullspace ES to also output the potentials and electric fields in a ParaView compatible format. As an example of how to turn on compression, that's very simple. We've done a lot of study about what the optimal settings are, and for the most part, the default settings will get you very far, and all you need to do is change that one keyword to say compress. The user guide goes into a lot of detail about all of the control parameters that are accessible for the compression solver, and so I encourage you, if you are running on a very large problem on constrained resources, you can look in the user guide for more information about that. And of course, you can always reach out to us at info@nullspaceinc.com. So once we run the simulation, we can move into post-processing. And post-processing is really very simple. Again, it's all a native Python. There's just a simple Nullspace ES Python module that you can import into your own Python environment. And throughout all of the examples, you'll see a recipe that is basically 4 commands. There's a command to extract the electrodes that were actually simulated in that simulation. There's a command to extract a grid of XYZ points. So we tell it the grid ID, and we get out the XYZ points for that grid. And then for a given grid and a given electrode, we can extract the potentials and the electric fields. And all of these arrays that come out, all of these data structures that come out are standard Python NumPy arrays. There's nothing proprietary about our data structures or anything like that. We're trying to maximize the flexibility that you have as a user to manipulate the data in any way that is convenient for you. So we want, in this example, to form something proportional to the pseudopotential, so just taking the magnitude of the electric field and then querying for indices into the grid at the y=0 location and at the location where we think the height of the pseudopotential null is. All of our examples that we provide are in matplotlib format. However, you're free to use any plotting package within Python that is convenient for you or that you prefer. And in this particular example, it's just a very simple example. We're plotting the electric field components and magnitude along X at the center of the trap and the pseudopotential height. And then in the second plot that we'll look at, it's a slice through the XY plane to visualize the pseudopotential null. And so we can just run that. And you see we get our two plots here. Just electric fields versus X at the pseudopotential height. So we would expect the EY component, if we go back and examine the geometry for the RF rails, the EY component should be 0, and you should have the EX trending like so, and a very mild EZ component. Since the geometry is finite, there will be some EZ component. And then if we examine the pseudopotential as a slice through the XY plane, we can see that the null height is at about 75 microns. So this is just a very simple example to demonstrate the very basic workflow of how you can access the data and how you might plot or manipulate the data. Let's say we wanted to do a parametric study, and so I demonstrated before how we had parameterized the number of DC electrode pairs that were in the trap, and so we want to, say, examine the behavior of the pseudopotential height as the trap gets longer. We know that if the trap is very short, the finite length effects are going to impact the behavior of the pseudopotential. And so basically how long do we have to make the trap before at the center of the trap the height has stabilized? And so we've run 4 different cases: 7 electrode pairs, 14 electrode pairs, 28, and 56. And you can see this was run on a sort of a basic engineering laptop, and at 28 and 56 electrode pairs, the trap was big enough that we saw a performance benefit in terms of runtime and memory from using the compression solver. So here we've got 2 problems that were run with the dense solver and 2 sizes that were run with the compression solver. And we're just going to loop over each one of these and perform a very similar set of operations. You can see I'm extracting the electrodes, extracting the XYZ points for that grid for a given electrode, extracting potential and electric field, compute the pseudopotential, and then we're just going to maybe do a little interpolation here to get a finer sampling in Z and plot how the pseudopotential height varies at the x=0, y=0 location. And you can see here, so this is at the center of the trap, moving up from the trap as we go along the x-axis, which is the z coordinate in this case. So you see with 7 electrode pairs, the null is at about 72 microns, 14, it's at, say, 74 microns. And then by the time we get to 28 electrode pairs, there's really not much difference between 28 and 56. So maybe for our purposes, in this simple example, we'll say that the pseudopotential height has settled out at 28 electrode pairs, and we will go about our analysis from there. So just a simple example. You can move to obviously much more sophisticated workflows from here, just leveraging these basic commands and this basic recipe. So in terms of visualization in ParaView, which I mentioned a moment ago, you can import the VTU file and the XMF file. The VTU file is the geometry, and here we can see I have selected to show block 2, which corresponds to the RF electrode. So we see the charge density on the RF electrode going to some positive value, some large positive value on the edges, and correspondingly these grounded electrodes are compensating by going to some negative value. And then in the XMF file, this is a visualization of the full 3D rectilinear grid, and we're just plotting the electric field magnitude, which is proportional to the pseudopotential, as a series of contours that have been clipped, so we can see inside the contour. So if these types of visualizations are helpful, this is accessible. Sometimes it's nice in ParaView, especially if you have an ion flight solver. You can couple that with these visualizations to make some really nice animations of the behavior of the ion, for example. Previously, I mentioned the ability to model discrete bodies of revolution. So a good example of that is a ring trap, and here we have an example from this dissertation. So if I just run that, we can see here that we have a central electrode and an outer ring that represent the RF electrodes, 2 ground electrodes, and then a DC electrode. And the RF and ground electrodes, as you can tell from the mesh, the way we have this set up, those are continuous. So we've got 8 pizza pie slices, if you want to think of it that way. And when these get chained together effectively through the symmetry condition, we have continuous electrodes going around in a ring. And then we can examine here this DC electrode. There's a gap, so half the gap width at this symmetry plane is represented, and of course we want to have a fine mesh there on the edge. And this is a good example again of how you can leverage the even and odd symmetry capabilities to be able to synthesize arbitrary DC electrode pairings. So we can run this trap with this 8-fold rotational symmetry in even and odd modes and still have flexibility in terms of how we synthesize DC electrode values. Again, it depends on your application, and you need to have an understanding of how your electrodes are electrically tied together, etc., in terms of how best to exploit the symmetry feature. But if you can model and exploit geometric symmetry that is compatible with how your electrodes are wired up, and take advantage of even and odd symmetry, you can get a lot of computational gains from that.